Hello, welcome to the session on embryo donation for ataxia research with human embryonic stem cells. It is my privilege to introduce our speaker today, Dr. Gary Smith, who is a professor of obstetrics, gynecology, physiology, and urology, and the director of the MStem Cell Laboratory and director for reproductive sciences for the Reproductive Sciences program at the University of Michigan. He completed his Ph.D. and postdoctoral training at Washington State University and the Oregon Regional Primate Research Center, respectively. He has been the scientific director of the Human-Assisted Reproductive Technologies Laboratories for 30 years at institutions such as the University of Chicago, University of Michigan, and Baylor College of Medicine. His work on stem cells spans and links areas including political and public policy and engagement involving human embryonic stem cells, the derivation of disease-specific human embryonic stem cells with national and international distribution, fostering cross-discipline collaborations using disease-specific human embryonic stem cells to understand molecular mechanisms of congenital birth defects and adult diseases, and practical solutions to enhance clinical utility of human embryonic stem cells in drug testing and therapies. Dr. Smith was a participant in the drafting of the Michigan Proposal 2008-2, which proposed to amend the Michigan State Constitution to remove restrictions on embryonic stem cell research. With the passage of Michigan Proposal 2008-2, Dr. Smith established the state's first human embryonic stem cell derivation laboratory in 2009, now called the MStem Cell Laboratory. The University of Michigan's MStem Cell Laboratory has become the leading U.S. institution in the derivation of disease-specific human embryonic stem cells with the acceptance on the NIH Stem Cell Registry. These disease-specific human embryonic stem cell lines represent human cell models for mechanistic studies of congenital birth defects, establishment, and progression. Additionally, there are disease-specific human embryonic stem cells. These support novel means of screening new therapeutics and repurposing drugs for disease-on-a-dish models for potential treatments for single gene disorders, including different forms of ataxia. And with that, thank you so much for joining us, Dr. Smith. The floor is yours.
Great. Thank you very much, Celeste. And thank you for the NAF for inviting me to speak with you today. As indicated, what I'd like to do is talk a little bit about human embryo donation for ataxia research, utilizing those embryos to establish human embryonic stem cell lines, and then how those can be used to further our understanding about monogenic diseases such as ataxias. So as I get started, I'd first like to say that I have a few disclosures. I do jointly own multiple patents with the University of Michigan in assisted reproductive technologies, stem cells, and a bioengineering technique called microfluidics. And I am a stockholder and a scientific advisor for Overture Life, a microfluidic company in the UK, US, and Spain. But none of the things I'll talk about today are related to any of the Overture Life progress. So real quickly, just as an outline of today's discussion, first like to talk about human embryonic stem cells, or what we call hESCs. We'll have some definitions here. We'll talk a little bit about political landscape. I am fully aware of both the political and social differences that there may be and the ideas of how we can use human embryonic stem cells. And then we'll talk about how we derive them. Within that, we need to talk a little bit about in vitro fertilization and embryo genetic testing, and then how those embryos that are tested and found to be affected are donated to the research of human ESL derivation that we perform. We'll talk a little bit about some of the monogenic disease-specific human ES cell lines that we have produced and how we collaborate with researchers across the United States and really now across the world in trying to understand some of the effects or some of the causes and consequences of these monogenic diseases using these human embryonic stem cell lines. And then at the end, happy to have a discussion and answer questions or attempt to answer your questions. So I like to use this slide to begin with because we always throw in it at the end of a talk, and sometimes we're rushed and that, but it's really the people that work in our laboratory They give me the freedom to talk about the things that we are able to accomplish. And so many of the people are listed here in the acknowledgements, postdoctoral fellows, MDs, PhDs, PhD students. In my laboratory over the last 30 years, we've had about 70 different postdocs and doctoral fellows that have worked on different areas of egg, sperm, embryo, and embryonic stem cell work. Faculty that we collaborate with, our laboratory is firmly believes and has worked towards the idea of breaking down silos between different disciplines, and with the idea that when we put people together with different expertise, that really opens the door for new ideas and discoveries. And so you'll see here many faculty members from the University of Michigan that we work with in different areas, very basic areas, biomedical engineering, hydrogels, but specifically with regards to this talk is really working with disease-specific researchers, because that's not our expertise. Our expertise is cell biology and embryo work and things like this, but I'm not an expert in ataxia, and I can't be an expert in ataxia. But whenever we derive a stem cell line, we reach out to those around us that do study these diseases. And you'll see our work is really trying to facilitate the use of these resources to be able to advance our understanding of diseases. So we've done that with hypertrophic cardiomyopathy, in cardiology, with SCA3, with Dr. Hank Polson and others, Fragile X disease, spinal muscular, bulbar muscular atrophy, and so on listed here. So we're going to introduce a lot of newer ideas, and it's going to jump around a little bit, but we have to do that to try to make the story come together. So the first thing is to think about stem cells. Well, the area of stem cell biology has advanced significantly over the last 2 to 3 decades. It's important to recognize stem cells are part of our body. It is nothing new. We are losing millions of cells every day. And if we didn't have stem cells within our own bodies, we would lose the gut, or the gut lining per se, in 2 days, our skin in 3 weeks, and red blood cells in 4 months. So these are cells that are inherent in our body. And we'll talk about the different types of stem cells. But while we're advancing our knowledge of stem cells, it's really something that is part of our body. So with a definition, what makes a stem cell a stem cell? Well, the cell has to have the ability to self-renew. It has to be able to replicate. And here we see human embryonic stem cells. This is a colony of thousands of human embryonic stem cells. And so these cells have to be able to grow and renew. While they grow and renew, they have to be able to maintain a normal chromosome number, so their genetics stays the same. This is very important because many cells, when they replicate over time, their genetics get altered, and sometimes that can cause cancers. So stem cells replicate, keep their genetic material the same, but the most important thing here is that these stem cells, or these cells, have the ability to differentiate to cells that are different in their function and their characteristics in comparison to the original cell. So the cell replicates, it stays genetically normal, but with the correct conditions can differentiate into another cell type. So making it a little more complicated, there are different types of stem cells. If we look at the 3 different types, there are what we call human adult stem cells. We say these are multipotent because they can't become any cell of the body or the organ. They can just become certain cells within a specific organ system. Example of this is hematopoietic stem cells, or blood stem cells. And this is something that's been known since the 1950s. Don Thompson at University of Washington actually derived the idea of being able to do transplantation of blood stem cells to be able to replace old stem cells. The other category is human embryonic stem cells. We'll talk about that. These are what we call pluripotent. They can become every cell of the human body. They have that potential to become every cell of the human body. These were discovered in 1998, so not that long ago, by James Thompson. The third type is human-induced pluripotent stem cells, or what we call iPS cells. This is a great story. Shinya Yamanaka, I've been to his laboratory at Kyoto when he was working on this. It was really a great project that he really worked on, trying to understand how you could reprogram a cell that is completely differentiated, like a skin cell, into a cell that might act like a human embryonic stem cell. And I remember being at his first talk in 2005, 2006, and nobody believed it. And researchers went back to their labs and tried to repeat it and were able to repeat it. And these are very important stem cells, but they're not the ones we're going to talk about today. So the important thing to recognize is that within these types of stem cells, they're all called stem cells, but they're not all equal. And so the analogy I use is, here we have three different animals: Grace Kelly, my dog, a hippopotamus, and a giraffe. Yes, they're all animals, yet they are not all the same type of animals. And I would say that the same is true with human embryonic stem cells in regards to induced pluripotent stem cells and in regards to adult stem cells. So they share similarities, but they're not absolutely the same. So as I mentioned, today we're going to focus on human embryos and human embryonic stem cells. And so I'll just go through a little bit of basics of human embryo development and how we derive human embryonic stem cells. So these are different stages of human embryo development. Each of these embryos is about 120 microns in size, so it's smaller than the period at the end of a sentence. But we first start out with the fertilized zygote that then in one day will develop to a 2-cell embryo, to a 4-cell embryo, to an 8-cell embryo on day 3. 4, the cells start to come together to form what we call a morula. And then on day 5, we'll see this blastocyst, where you have these cells out here that we call trophectoderm. This area here is called the inner cell mass. The trophectoderm in the further developing fetus will become the placenta, and the inner cell mass will become the fetus proper. This here is about, I'm going to say, about 150 to 200 cells on day 5. And then on day 6 and 7, this blastocyst will hatch out of a shell called the zona pellucida. And this hatched embryo is then the embryo that, if it's in the uterus, can actually begin to implant into the uterus. So when we look at derivation of human embryonic stem cells, we have our 2-cell embryo that then becomes on day 5 what we call the blastocyst. The trophectoderm becomes the placenta over time. And this inner cell mass by day 14 will become different parts of the fetus: the endoderm, the mesoderm, and the ectoderm. When we make embryonic stem cells, we collect the cells on day 5, the inner cell mass, and place them into culture under conditions will allow them to expand, replicate, as I said, stem cells do, but we have to keep them undifferentiated. We don't want them to start to differentiate. So we have conditions that over time we've derived that actually can keep these cells dividing, but they don't differentiate into endoderm, mesoderm, or ectoderm unless we want them to. And that's important when we talk about experiments, and we'll talk about that. So jumping around a little bit, we need to talk about in vitro fertilization because we can't make human embryonic stem cells without the human embryo. And the only way to get the human embryo is through in vitro fertilization. So just quickly, a 101 outline of what IVF or in vitro fertilization is like. Remember, the woman will have hormonal stimulation for 10 to 12 days. This is to cause multiple eggs to develop. When the eggs are retrieved on day 0, or the oocytes are retrieved, on average, let's say there's 13. Then, the same day, sperm is collected. The sperm and the egg are put together at insemination. The next day, in the laboratory, we look for fertilization. Here you can see this is normally fertilized. And then we place those embryos into growth media that will allow them to grow for the first 5 days. On day 5, as I mentioned, we should have a blastocyst in trophectoderm and the inner cell mass. This embryo, if it's in being used for treating infertility, can be transferred as a fresh embryo. They can be frozen. The thing that I want to introduce now, which is again a little, maybe a newer concept, is that nowadays in treating infertility and even in just basic in vitro fertilization, about 70% of the cases, at least in the United States, undergo what is called pre-implantation genetic testing. And this is where a few cells from this embryo can be removed and then can be tested for the correct number of chromosomes, or, as I'll tell you here in a second, for monogenic diseases. And so when this occurs today, like I said, 70% of cases have this. And when this happens, all of the embryos are cryopreserved. So they're all frozen. This gives the labs the time to do the genetic analysis. And then, knowing what the genetic makeup of the embryo is, then those embryos that are normal can be used to try to establish a pregnancy. So I'm going to go ahead. I know there's a lot of information here, but I'm going to go on just quickly. Different types of genetic testing that can be done. PGTA is for normal number of chromosomes, let's say like for Down syndrome of trisomy 21 versus normal number of chromosomes. PGTSR is for translocations or inversions of parts of chromosomes. Today, what we're focusing on in this talk, and really our lab focuses on primarily, is genetic testing that's done for monogenic diseases. So this is screening embryos, those few cells that are taken out of the trophectoderm, for diseases like cystic fibrosis, Huntington's disease, BRCA1, BRCA2. In the ataxias, there's testing of human embryos for many of the SCA3s, SCA1, SCAs, also Canvas, and also Friedreich's ataxia. So this is very important because I think this is what I want you to understand is we are focusing primarily on acquiring embryos that are tested independent of what we do for monogenic diseases. And there's now 400 to 500 different monogenic diseases that are tested for in human embryos. So when we look at sources of human embryos for our human embryonic stem cell derivation, of course, there are couples that are doing in vitro fertilization to build their family. Let's say this family, they have 9 embryos, they have 7 children, they don't want to have any more children, they have frozen embryos, and now they have to make a decision, what do they do with those frozen embryos? They can keep them frozen. It's their choice if they want to discard them. They can donate them to other couples through sources that exist nationally and internationally, or they can donate them to research. The group that we are most interested in, and I think this is very important because this is the group that a lot of people don't think about. these are many times couples that have no infertility whatsoever. They are doing in vitro fertilization to be able to have embryos in the lab that can be tested with pre-implantation genetics for monogenic diseases. And these are diseases they know they have in their family. And so they're doing this to try to avoid a potential birth defect in their child. And this is done really very common across the United States and across the world. So in each one of these cases, when you do a testing of these embryos, let's say for Fragile X or SCA3, there's going to be normal embryos that can be used to try to establish a pregnancy and not pass on that genetic abnormality. But there are also affected embryos. These affected embryos are not really feasible for adoption to others, and they're almost always discarded. And what we've done is said, instead of discarding these embryos, donate these to research in which we can now make a resource available, a human model system to be able to study these different diseases. So let's talk about human embryo donation. And again, I'm focusing now on PGTM tested and affected embryos. So when I talk to somebody just on the street and we talk about this subject, I find most people don't recognize that every one of these embryos that we use would otherwise be discarded. And so what we are doing is making a pathway forward to donate these embryos. We need to know the genetics of the couple. They need to do in vitro fertilization to generate the embryo in the lab, because that's the only way that you can do the genetic testing of the lab. And so, like I said, many times these cases are in couples that do not have infertility. They're very fertile. They're just doing this so that they can stop movement of that genetic abnormality through their families. For you as individuals that are thinking about this, it's essential to be proactive. I've worked in the fertility healthcare industry for 30 years. I think it's amazing things that have been done in this area, but the focus is primarily on helping people have children. But if you know that you have a monogenic disease and you want to do IVF with PGTM, you need to tell that to your healthcare provider. Many of them will not offer you the opportunity to donate the tested and affected embryos. And so that's why I think a discussion like we're having today is so important, because I think many people don't know that this opportunity exists to donate this. And I find when I talk to people across the country, I can think of a couple in New York that donated their Fragile X embryos for our stem cell derivation. And they were excited about that because, she had a brother who had Fragile X. And she said, why would I discard these Fragile X embryos if I can donate them to something that can potentially help my brother or others in the future with Fragile X? So we suggest you contact MStem Cell Lab before your IVF cycle begins. We do this I'm not going to say every day, every week. We consent people for donating their embryos. We have an informed consent that's been worked on, has worked very well for the last almost 20 years. We have a couple forms that the fertility healthcare provider has to sign and return to us. And part of our IRB approved study is that couples have to physically talk with our program manager. She has to be able to demonstrate that she's answered any questions that the couple has. Last thing I'll mention here is that when donations occur, MStem Cell Lab and the fertility healthcare provider will organize the shipment of the tested and affected embryos from wherever they are in the United States to our laboratory at the University of Michigan, where we will work on those affected embryos to try to make human embryonic stem cells. For those of you that are interested, I give you this information here of our website. You can go through kind of the stem cell process, some of our publications, some of the stem cell lines that we have, and there's a specific area here that talks about how you can go through embryo donation. As I mentioned, many healthcare providers don't necessarily know that this is something that is available. And so I believe, this is something that you need to be proactive about and be able to let your healthcare provider know that this is something you want to participate in. I put here a publication we had last year in fertility and sterility. This is the primary publication from the American Society for Reproductive Medicine. At this point, I will make a point because I know I heard somebody who was from Denmark and different places. I have to say our IRB only allows donation of embryos in the United States. So they have to be from somebody in the United States and a healthcare provider in the United States to us, not from Canada, not from Denmark. So it does have that specificity. But in actuality, there's over 460 different clinics in the United States that actually could make donations of affected embryos to our program. And this paper here demonstrates that and talks about how it can be done. So, this is something I would suggest if you are doing IVF and PGTM for an ataxia and want to donate your affected embryos to derivation, that this is a paper that I would show to my healthcare provider, my fertility healthcare provider. So let's talk a little bit about the promise of human embryonic stem cell research. What most people think about is the potential of using stem cells for regenerative medicine, to use a stem cell to make bone marrow, to make nerve cells, to make cardiomyocytes, to make pancreatic cells, to treat different diseases. So that's what we call this field of regenerative medicine, devoted to treating using stem cells to differentiate them into a specific type of cell, and then use that to repair damaged or destroyed cell tissues of that organ. And I think this is something that will be exciting and will be fruitful in the future. But that's not what we work on per se. We are looking at using stem cells really to study how cells differentiate and try to understand and prevent the formation or the effects of birth defects, and how we can understand these monogenic diseases to be able to either treat these diseases or alleviate them. And so this is really what we call disease modeling. And this is important because many times mice, rats, monkeys, they don't model many of these diseases correctly. And so this is an actual way, by using human embryonic stem cells, that we can begin to model these different diseases. So this idea of regenerative medicine, I don't ever want to say it's not something that we should be pursuing. I think it is. It's not what my laboratory works on. But I get involved in some of this because this is what the public really hears about. An example here is Gordie Howe, who played hockey, had a stroke. NPR radio did this discussion in 2015. The Howe family were very impressed with the stem cell transplant and treatment that he had in Mexico. Unfortunately, it did not necessarily work, and he has passed away. But I think it's an example of there is promise here, but we need to do clinical trials. And as a scientist and a clinical scientist, I believe in evidence-based medicine. And so for things like regenerative medicine, we're far away from having safety studies, efficacy studies. We don't want it to be anecdotal. We need to have publications peer-reviewed, and there needs to be FDA approval. So I bring this up because it's important, because there is a lot of hope and hype in the use of stem cells for things like regenerative medicine. But as I said, that's about all I'm going to say there. And now I'll talk really more about using human ES cells to model single gene disorders. So you can think about this as a human disease in a dish. So we know that specific genetic abnormalities, monogenic diseases, or an aneuploidy, an extra chromosome like trisomy 21, causes abnormal cells, organoids, organs, or systems, okay? But how that happens, how that genetic abnormality gives rise to the abnormal neurons or muscle cells is not understood, and it's a black box. But with these human embryonic stem cells that we know because they were genetically tested and have been found to have the abnormality, let's say that contributes to SCA3, then we make those embryonic stem cells. The stem cells themselves are not investigatively important. They are a source. So then we can direct those cells to become neurons in the laboratory. And when we do that, we can then study how they develop normal neurons and how they develop abnormal neurons. And so what I would propose to you is really that by having these types of cells, we can open up this black box, gain knowledge, and that in and of itself is going to lead to treatments and cures of the future. So again, this is where it's not just about our research. Strength to me is when we take our expertise in stem cells, we make a resource available and work together with a disease-specific researcher in a collaborative way to be able to advance our knowledge of science and these diseases. So one of the things I want to mention here is I'll just go back a little bit in history, because I think this is important because it talks about what a lot of the misunderstandings of human embryonic stem cells. So before 2008, Michigan, like Louisiana, had the most restrictive laws on human embryonic stem cell research in the United States. 2004, the president of the University of Michigan, Mary Sue Coleman, put together a panel. I was on that panel, 11 other people, to write a proposed modification to our state constitution. Took a couple years to write it, took a couple years to get it on the ballot, but in 2008, it went on the ballot. And a couple of things that were in that proposal are listed here. It was proposing to expand the use of human embryos for research permitted under federal law. So if it's not allowed under federal law, it can't be done in Michigan. Subject to the following limitations. The embryos have to be created for fertility purposes. They are not suitable for implantation, such as genetically abnormal or an excessive clinical need, would be discarded unless used for research, and are donated by the persons, both the sperm donor and the egg donor, who are seeking fertility treatment. In addition, Prop 2 stated that it prohibits any person from selling and purchasing human embryos for stem cell research. These are all things that passed, and we helped write those into this, and we follow them by the letter. There is no reason not to follow these regulations. And it passed, as I said, in 2009. That opened up the door for us to start making human embryonic stem cells in the state of Michigan. We follow, at that same time, some of you in the United States will recognize that also President Obama was elected at that time, that the removal of the number of stem cells that could be used for research was taken away. And in essence, new guidelines came in and said, well, there's 16 different things. If you make a stem cell line, you have to demonstrate that you follow these rules. And so every single stem cell line we make, we demonstrate, we submit these 16 how we follow these 16 rules to the National Institutes of Health. They review it, and then they accept it on the NIH registry, or they don't. If you didn't follow the rules, they don't accept it. The importance of this is once the cells are on the NIH registry, these cells can be studied with federal dollars. So this is something really most scientists don't even understand. This is very convoluted, if you will. But if you make a stem cell line and you follow the guidelines and you document it and they get reviewed and accepted on the registry, now any researcher in the United States can use those stem cells with federal dollars to study the specific diseases that might be of interest. However, there is still an amendment that is in the federal Constitution that says no federal funds can be used for research in which a human embryo is destroyed. And this is where the controversy exists, because the embryos that we use to make the stem cells are destroyed. So it's not illegal to do this, but we cannot use federal funds to be able to do this. And as I said, every one of these embryos that are disease affected or otherwise discarded. So we're almost like a lost leader. We can't use federal funds to make the stem cell lines, but as long as we do it correctly, follow the regulations, then they can be used with federal funds. Very confusing. So why study human ES cells? I have people ask me this all the time. It would be a lot easier to use iPS cells, but human ES cells are the gold standard. Inherent in those cells is to become every cell of the human body. We may not know how to make every cell of the human body in the laboratory, but in essence, inherent in those cells is that they can. Induced pluripotent stem cells, as I mentioned, are similar to human ES cells, but it has been shown since they come from skin cells, they have developmental epigenetic memory and therefore have some genetic instabilities and lack what we call plasticity. They don't have that ability many times to become every cell of the human body. The other thing I would say is that actually there are resource ethical reasons. I believe, and we can discuss this, I believe it's almost unethical not to use these embryos that are being tested for monogenic diseases that are being discarded. And like I said, almost every single case, when you test for a monogenic disease, there are affected embryos. And so thinking about donating those to research on specific diseases, I think is a resource reason to do this. The other thing I'll mention is I personally have personal reasons. My personal reasons is that I have always believed in service-oriented research. And I come from a family of firefighters. My grandfather, my father, my uncle, my brother. I think I have now 2 nephews and a niece that are firefighters in California. And I was the only one really that went to college. But as I did, I always had that idea of service-oriented research. I think it's what drove me to fertility treatments and things like this, is because I wanted to be able to use our research and our science to try to better improve the chances of people being able to have children. But after a few decades working in the fertility area, I kind of started to ask the question how I might be able to use skills and knowledge that we have in embryology and IVF to have a more widespread impact on human health. And when I asked myself that question, the answer that kept coming in is yes, we could use our experience in embryology and IVF to improve the derivation of human embryonic stem cells and make those available to many researchers to study all different types of diseases. So here's just a list of some of the goals. I've kind of gone through these. We want to make new monogenic disease lines and be able to collaborate with other people to be able to move the knowledge and the treatment of these diseases forward. Another thing that I've been able to participate in is engaged in educating the public and research communities of pros and cons of human ESL research. I think, many times we want to take the easiest path forward, and I would tell you, it's a lot easier to work on induced pluripotent stem cells than human ES cells. But personally, I don't believe we need to make a decision of going one direction or the other, that we can do both. And by doing both, someday down the road, we're going to see that iPS cells let us do things that we can't do with human ES cells, and human ES cells let us do things that we can't do with iPS cells. So those are some of the goals of our laboratory. We have extensive oversight listed here, IRB approval. We have a university HIPSCRO committee that has to look over everything we do. We have informed consent. We have to do a yearly Michigan Department of Health and Human Service report. And as I mentioned, when we make a stem cell line, we submit those documents to NIH. And I would have to say we're very proud that every stem cell line we have submitted to NIH has been accepted on the registry since the first one that we made in 2012. I don't expect anybody to memorize this, but this just goes through and shows the different types of human embryonic stem cell lines that we've made for monogenic diseases. And so I think there's over 50 now, 52, 53, 54 lines that we have made for monogenic and aneuploid embryos. You can see here 134.1 is for SCA3. Dr. Lauren Moore has done some of her work on that stem cell line. You can see some of these have multiple lines for different diseases. Some are from the same family of embryos, so embryos that were donated from the same family. As you can see, all of these stem cell lines are de-identified. So that's an important thing that we do in our derivation is the donation has to be done by the couple, but once the donation is made, the embryo itself and the stem cell, if we derive it, are de-identified and not linked to any couple. We have to fully characterize these embryonic stem cells. This takes about 7 months for each one of the lines, maybe 6 months if we're lucky, but we have to demonstrate that they're genetically normal. We have to demonstrate that they have that potential to become every cell, or at least different types of cells, what we call pluripotency markers, and that they actually can make mesoderm, endoderm, and ectoderm. If they can't do these things, then they're not truly a human embryonic stem cell. So these are things we test before we ever get this out into the hands of a disease-specific researcher. So these are just a couple examples of some of the different embryonic stem cells that we've made. We've made ones for hypertrophic cardiomyopathy and published papers working together with cardiologists on these human embryonic stem cells. When you make them into cardiomyocytes, when they come from the diseased stem cell line, they make larger cells. They have abnormal function. They're sarcomeres, which cause them to contract. They contract in the laboratory. They don't contract properly. And we're able to actually demonstrate in this publication that we could correct the gene in the stem cell and correct the function of the cardiomyocyte when it beats. That was in 2016. We also have studies that we're doing on Down syndrome right now. These are very exciting studies looking at GABAergic neurons that come from individuals with individual stem cell lines with trisomy 21. The idea here is that the GABAergic neurons are a neuron that quiesces function, and that we are hypothesizing that they are overactive GABAergic neurons. And so we can take these human ES cells and in 75 days, we can make them into GABAergic neurons. And then we study how the stem cell functions when it comes from a trisomy 21 human embryonic stem cell, or if it comes from a normal stem cell. So The important thing I want to focus on here is that the embryonic stem cell, as I said before, itself is not the interesting thing to study. The embryonic stem cell has that ability to make cells where the disease is found in a cardiomyocyte, in a neuron. And then we can study those neurons when they come from an embryonic stem cell, let's say with SCA3, versus whether they come when they come from a stem cell without the expansion that gives rise to SCA3. So this was the embryonic stem cell line that we've made for SCA3. I still believe it's maybe the only one in the United States, and I know it's the only one in the United States, maybe in the world. You all know more about SCA3 than I do, but we've been able to work with Dr. Paulson, Dr. Moore, Dr. Costa, and Dr. McLaughlin, really in trying to look at how the CAG trinucleotide repeat gives rise to abnormal neural function. So as I end, I'd just like you to think about these human embryonic stem cells really being an enabling resource to all different types of research in many different types of monogenic diseases. Neurosciences such as ataxias, ALS, SMA, cardiomyocytes or myopathies like I talked about, pediatrics, vision. We've made stem cell lines for Batten's disease, from Usher's syndrome, sickle cell anemia, and in cancers. So we believe that working on this, while it can be controversial, is important. The other thing I want to point out is recognize that these cells, as I say, can replicate and we can freeze them down. So these stem cell lines actually are an everlasting resource. These stem cell lines that we derive will be here long after I am gone, you are gone. They have that ability to actually be able to work for decades and generations. And so those are some of the reasons that we have stayed focused on this plan. Last thing I'll kind of mention here is funding acknowledgements. As I said, all of our derivation work can't use federal funds, makes it very difficult. We have to use private funds, foundation funds, and local funds to be able to do this. We've been very fortunate that the university has been supportive of this, from a philanthropist, Alfred Taubman, to the president of the university, many different deans and EVPMAs for the hospital, chairman of OBGYN, Tim Johnson and Dee Fenner. We also have gotten funding from ASRM, the American Society for Reproductive Medicine, and a joint institute to work together with Peking University. But with that said, I will just end with saying donations for the work that we do. Embryo donation, when you have tested and affected embryos, we do it every other day, once or twice a week. Those are always appreciated also. So happy to answer any questions you might have.
Wonderful. Thank you so much, Dr. Smith. That was very informative. We already have some submitted, so we're going to jump right into them. So the first question we have from an attendee: can frozen embryos be donated even after years in storage?
Absolutely. That's a great question. That kind of comes to that last point I made, where these cells, once we make them, we freeze them and they're going to be around forever, just like human embryos. So, we've taken our expertise in human embryology, and in my laboratory was a lab that really did a lot of the early work on how to freeze women's eggs. And so we've taken those technologies and we use them for the stem cells. So yes, if your embryos have been frozen for 2 years, 5 years, 10 years, doesn't really matter. It's simpler to do your donation if you do the paperwork ahead of time. But we have for sure done it with people that have frozen embryos. You just have to work through your previous healthcare provider.
That makes a lot of sense. We have a related question. Do you also accept unaffected embryos if I have several remaining after finish building my family?
Great question. And we we built the program to be able to get unaffected. We find we don't use as many unaffected to do our derivation as we do the affected. And so we don't accept those any longer. Our goal is not to have a stockpile of embryos. That's not what we want. We want to be able to get donations and use them. So we try to always make a stem cell line with every affected line we make, so we have a control. So we do still use some of those unaffected embryos, but today, if you go to our website, you'll see we're only accepting monogenic disease tested and affected embryos.
Okay, well, thank you for explaining that. And it might partially answer this question, but I'll ask it anyway just to make sure. We have an attendee who shares that they've gone through several rounds of IVF with PGT testing, just both PGT-M and PGT-A.
Yes.
And they have, can embryos be donated that are aneuploidy, that have those chromosome aberrations? What are your policies on that?
Yeah, great question. And I know this because of course, this is still my field also. So we try not to accept PGTA abnormal, PGTM abnormal.
Okay.
Because if we make that line, we can't really then determine if the abnormalities come from the monogenic disease or from the aneuploid disease. So at this point in time, one, we don't accept aneuploid donations. We have, and like trisomy 21, we have projects. So we do take in trisomy 21. But one of the things, maybe too much information, but we find that many of the aneuploid embryos don't give rise to stem cells because they don't have necessarily that ability to become a stem cell line. Trisomy 21 is one that kind of makes sense, does, because it's compatible with birth, right? So it makes sense that does. So specifically to the question, right now we're only accepting euploid monogenic disease lines.
Thank you for clarifying that. And you spoke about this a little bit in your presentation, but if you could reiterate, if someone chooses to donate, how will their identity remain protected?
Yeah, so we as receivers have to know identity, but that identity stays with us. Okay. The other thing I might mention real quick that's related to that. And so once we get it, it's in our files, but it doesn't go any further. In the consent, there's an area that asks specifically, if we derive a stem cell line, can we reach back to you for information in the future? We haven't ever done it, but we can see a value of that because having genetic history, family history, things like that might be important. And I would say 90% of the people say yes to that, but that's your choice. You can say yes or no.
Good to know that's part of the consent process. We have an attendee who is sharing some experience that her daughter has had, and how there's some people with ataxia that are at late onset that they don't want to know their genetic status, but they want to have ataxia-free embryos, so they undergo pre-implantation genetic testing.
Yep.
But her daughter's getting a little bit older. She was wondering if there's an age limit for egg collection in terms of that process and donation as well.
So there's two things I want to address here, because the first part of it was really good, is the anonymous donations. And just like I said, so we have that question in our consent. Can we reconnect with you if we make a stem cell? And what we found when we reviewed these, about 5 or 10% said no. And it was very obvious when we thought about it. Those are people that do non-disclosure PGTM, especially for things like Huntington's disease. Just like you're saying, people will be tested, but they don't want to know whether or not their embryos are affected, but they want to make a donation. So they can make a donation of their affected embryos, but they will never know that. So,
okay, that's very good to know.
The other side of that question is the age. And we have never set up an age limit. I would say that we don't have an age limit, but the likelihood of being able to have a euploid embryo has the monogenic disease is highly reduced in somebody of advanced maternal age.
Okay, good to know. We have a follow-up on one of the questions I asked. I didn't quite ask it properly. Regarding the euploid embryo question, do you accept mosaic embryos?
That's another great question too. And again, this being my field, we do a lot of research on mosaicism. And the problem right now is mosaicism is not, it's a little muddy. It's not black and white. And so when we're making a resource to be able to get out into the hands of other people, we want to, and again, like I said, it takes us 6 months to make a stem cell line and probably $40,000 each line to make it. We don't want to invest that time and effort into something that at the end of the day we test and we say, oh, it's not genetically, it's not genetically defined. Yes, it might have the mutation, but now all of a sudden has an extra part of chromosome 3, which is mosaic. And we don't want that. And so for those reasons, we are not accepting mosaic embryos.
In that answer, you mentioned cost, and someone has asked, does it cost anything to donate their embryo?
It costs nothing to donate the embryo, as I mentioned in one of my slides, and thank you for answering it. You don't pay for it. You don't pay for the shipping. We pay for everything. We organize it with the fertility healthcare provider. Once you make your donation, it's a complete donation, and that's how it has worked for the last, I don't know, 12 or 14 years.
And then, are there any other labs like yours accepting disease-specific embryo donation?
I have to say, so I think there are. I think we are the largest program in the United States. Actually, there's one program in Israel that's larger than us, but we're almost the largest in the world. But there are other labs. I would say I know for sure UCLA, and I know for sure Cornell also has been deriving human embryonic stem cells. So if we had to, suggest to other people, that's where I would go.
Well, thank you so much, Dr. Smith. We are out of time for today, but thank you so much for joining us and sharing with us your time and expertise on this subject. We really appreciate it.
My pleasure. And again, anytime you have questions, my email address is there. Please feel free to drop us an email.
And to all of you who attended this past hour with us, we really appreciate you taking time out of your day to learn a little bit more about embryo donation. So wherever you are in the world, good morning, good afternoon, good evening. Have a wonderful rest of your day. Take care, everyone. Stay safe.